Right now, as you sit here listening to these words, somewhere else in the universe, now doesn't exist. Not later, not before, it simply isn't there. On a planet 20 light years away, if it existed, an observer moving fast enough relative to you could calculate that your future has already happened. Another observer moving in a different direction could calculate that it hasn't happened yet, that it may never happen at all, at least not yet, from where they stand. Two people, two different presents, two different truths about what is real right now, and physics says both of them are correct. This isn't a thought experiment dreamed up by philosophers. It falls directly out of Einstein's equations, tested and confirmed for over a century, and it leads to a question that has quietly unsettled some of the greatest scientific minds in history. What if the flow of time, the sense that the past is gone, the future is open, and only this instant is real, is not a fact about the universe at all, but a story your brain is telling you? What if time doesn't move at all? Why this question won't go away? Every human culture has built its understanding of life around the same assumption. Time moves. It carries us from birth to death, from cause to effect, from memory to anticipation. We plan for a future that doesn't exist yet. We grieve a past that's gone forever. Our entire emotional architecture depends on time having a direction, a flow. But when physicists write down the fundamental laws that describe reality, the equations of classical mechanics, of Einstein's relativity, of quantum theory, something strange happens. The flow disappears. The equations don't care whether time runs forward or backward, they work exactly the same either way. Run the mathematics of a collision between two particles forward, or run it in reverse, and both versions are equally valid according to the laws of physics. There is no equation for now. There is no term in physics that says, this moment is special and it is happening. And yet, contradicting his own theory, Einstein confessed to a grieving family that the distinction between past, present, and future is only a stubbornly persistent illusion. He wrote those words to comfort the family of his lifelong friend Michel Besso, who had just died. Einstein himself would die only a month later. Why would one of the most rational minds in history say something so strange at the most human moment imaginable? Because he understood something about spacetime that most of us never learn. In the equations that describe our universe, the past, present, and future may all exist, together, permanently, all at once. Newton's clock and the first crack. To understand how physics arrived at such an unsettling idea, we have to go back more than 300 years to Isaac Newton. Newton imagined time as something absolute, a single universal clock ticking away in the background of the cosmos, the same everywhere, for everyone, always. Under Newton's picture, if you and I are standing on opposite sides of the planet, our now is identical. Time flows at the same rate for both of us, like a river running beneath the entire universe, indifferent to what happens within it. For 2 centuries, this picture worked. It sent rockets to the moon in theory, predicted the orbits of planets, and matched everyday experience perfectly. There seemed to be no reason to question it. Then, in 1905, a 26-year-old patent clerk in Switzerland took the idea of absolute time and quietly destroyed it. Albert Einstein realized that the speed of light is the same for every observer, no matter how fast they are moving. That single fact, confirmed by experiment after experiment, has a devastating consequence. If the speed of light never changes, then time itself must bend to keep the numbers consistent. A person moving very fast through space will experience time differently than someone standing still, not because their clock is broken, because time itself is behaving differently for them. This is called time dilation, and it is not speculation. It is measured routinely. GPS satellites orbiting Earth experience time slightly faster than clocks on the ground because they are farther from Earth's gravity and moving at high speed. If engineers didn't correct for this every single day, GPS navigation would drift by several kilometers within hours. Every time your phone tells you exactly where you are, it's quietly relying on the fact that time is not absolute. Think of time the way you'd think of a road trip. 2 drivers leave the same city at the same moment. One takes the highway, the other winds through mountain back roads. When they arrive, their odometers show different mileage. Not because distance is an illusion, but because they took different paths through space. Einstein showed that people take different paths through space-time too, and just like the mileage, the amount of time each person experiences depends on the path they took. But Einstein's revolution went even further than bending time. It fused time together with space into a single 4-dimensional structure, space-time, and that fusion is where the real mystery begins, the universe as a block. If space and time are woven into one single structure, then a strange question emerges. We don't think of here as something that comes into existence and then disappears. Paris exists right now even though you're not there. It doesn't flicker in and out of reality depending on where you're standing. So why would now be any different from here? This idea leads to what physicists call the block universe theory, and also known as eternalism. In this view, the past, present, and future are not sequential events happening one after another. They are all fixed points within a single 4-dimensional block, like frames already printed onto a reel of film. Nothing in the block happens, it simply exists in its entirety, timelessly. Your birth, this exact moment, your death. In the block universe, all of them are equally real, equally permanent, equally present, just located at different coordinates in space-time, the way Tokyo and New York are both real despite being in different places. This isn't just poetic language. It comes directly from the mathematics of special relativity, specifically from a discovery made by Einstein's own former math professor, Hermann Minkowski, in 1908. Minkowski showed that space and time could be combined into a single four-dimensional geometry, and that simultaneity, the idea of two events happening at the same now, is not absolute. It depends entirely on how fast you're moving. This produces what physicists call the relativity of simultaneity, and it's the key that unlocks everything. Imagine two spaceships passing each other at high speed. Two flashes of light go off at different locations. A person on the first ship, using perfectly accurate instruments, calculates that the flashes happened at exactly the same time. A person on the second ship, moving relative to the first, calculates with equal accuracy, using the same laws of physics, that one flash happened before the other. Neither of them is wrong. There is no cosmic referee who can declare a single correct answer. Physics allows both realities to be true simultaneously. Now extend this to the entire universe. If simultaneity isn't fixed, then now isn't a universal line separating a fixed past from an open future. Different observers moving at different speeds slice up the four-dimensional block of space-time differently. One person's future can be another person's past. This argument even has a name. The Redike-Putnam argument, developed independently by physicist C.W. Redike and philosopher Hilary Putnam in the 1960s. They showed, using nothing but the accepted mathematics of special relativity, that if relativity is true, the future must already be just as real as the past. Not probable, not potential, real. Roger Penrose and the geometry of reality. Few scientists have taken this idea more seriously than the mathematical physicist Roger Penrose. Penrose is famous for many things: his groundbreaking work with Stephen Hawking on the mathematics of black hole singularities, his Nobel Prize winning proof that general relativity predicts the formation of black holes, and his unconventional theories about consciousness. But throughout his career, Penrose has consistently emphasized just how seriously we should take the geometric picture of spacetime that relativity gives us. For Penrose, spacetime isn't a convenient mathematical trick, it's the actual architecture of reality. In his view, treating the universe as a four-dimensional geometric object rather than a three-dimensional stage where events happen one after another isn't philosophical speculation, it's simply following the mathematics of general relativity to its logical conclusion. Penrose went even further with an idea that sounds almost mythological: conformal cyclic cosmology, or CCC. In this hypothesis, the universe doesn't just have one beginning and one end. It may go through an endless series of cycles where the extreme heat death of one eon, stretched infinitely thin, becomes indistinguishable from the extreme density of the next Big Bang. Penrose has even pointed to unusual circular patterns in the cosmic microwave background, the faint afterglow of the Big Bang, as possible evidence of a previous cosmic cycle imprinting itself onto our own. It's important to say clearly, CCC remains a highly speculative hypothesis. Most cosmologists are not convinced, and the circular patterns Penrose identified have alternative, more conventional explanations. But the fact that a scientist of Penrose's caliber is willing to propose that time itself might loop rather than simply flow forward forever tells you how open this question still is. The one place where time seems to truly flow. If the fundamental equations of physics don't distinguish between past and future, why does the universe feel so overwhelmingly one-directional? Why can you remember yesterday but not tomorrow? Why does a shattered glass never reassemble itself? The answer lies in a quantity called entropy, a measure of disorder, first formalized in the study of thermodynamics in the 19th century. The second law of thermodynamics states that, in any closed system, entropy tends to increase over time. Disorder grows, structure breaks down, heat spreads out evenly instead of concentrating itself. This is the closest thing physics has to a genuine arrow of time. Eggs break instead of unbreaking. Coffee cools instead of spontaneously heating up. And crucially, we remember the past, a low entropy, more ordered state, but not the future, a higher entropy, more disordered state, because memory itself is a physical process that only works in the direction of increasing entropy. But here's the deeply strange part. Entropy doesn't explain why time flows, it only explains why disorder increases in the direction we call forward. The underlying laws of physics governing every individual particle collision remain perfectly reversible. The arrow of time isn't built into the fundamental laws, it emerges from the extraordinarily improbable fact that our universe began in an extremely low entropy state near the Big Bang. This raises an unresolved and genuinely unsettling question in cosmology. Why was the early universe so improbably ordered in the first place? Physicists call this the past hypothesis, and it remains one of the most significant open problems in the foundations of cosmology. We don't fully know. We only know that if it hadn't been true, memory, causality, and the felt experience of time passing might not exist at all. What quantum mechanics adds to the mystery. Just when relativity seems to suggest that time doesn't flow, quantum mechanics complicates the picture even further. In quantum theory, particles exist in superpositions, combinations of multiple possible states, until a measurement is made. At the moment of measurement, the wave function appears to collapse into one definite outcome. Many physicists have interpreted this collapse as something genuinely new, happening in time, an irreversible, one-directional event that looks very different from the reversible mathematics of relativity. This creates real tension at the frontier of physics. General relativity describes gravity through a smooth, unchanging four-dimensional geometry in which nothing becomes. Quantum mechanics, in many interpretations, seems to require moments where new facts about reality genuinely come into existence. Reconciling these two descriptions is part of the unsolved challenge of quantum gravity, one of the deepest open problems in all of physics. Some interpretations, such as the many worlds interpretation, avoid the idea of collapse altogether, proposing instead that every possible outcome occurs, each in its own branching universe. Other interpretations, such as objective collapse models, an area Penrose himself has contributed to with his gravitationally induced collapse hypothesis, propose that gravity itself might be the trigger that forces quantum possibilities to become definite reality. Under Penrose's proposal, sufficiently large quantum superpositions become gravitationally unstable and collapse spontaneously, potentially linking the mystery of quantum measurement directly to the geometry of spacetime itself. It's important to be honest here. None of these interpretations have been experimentally confirmed as uniquely correct. This remains one of the most actively debated open questions in physics. The debate physics hasn't settled. So which is it? Does time genuinely flow, moment by moment, bringing new reality into being? Or is the flow of time an illusion generated by consciousness layered on top of a static, unchanging four-dimensional block? Physicists and philosophers remain sharply divided. Advocates of the block universe, or eternalism, argue that relativity leaves no room for a universal flowing now. If simultaneity is relative, they argue, then privileging one particular moment as uniquely real, while others are merely not yet real, contradicts the mathematics that has been tested to extraordinary precision. Critics, often called presentists, argue that only the present moment is real, and that the past and future exist only as memory and possibility. Some point out that quantum mechanics, with its apparent moments of genuine becoming, undermines the pure block universe picture. Others argue that consciousness itself may play some fundamental role that our current physics simply hasn't captured yet. There is also a middle position, sometimes called the growing block theory, which suggests that the past and present are real and fixed, while the future remains genuinely open, added moment by moment as it comes into being, like new pages being added to a book whose earlier chapters can never be rewritten. No experiment has yet definitively settled this debate. It remains quite literally one of the deepest open questions about the nature of reality itself, what modern science is discovering. Modern experiments continue to probe the edges of this mystery. Atomic clocks, accurate to within 1 second over billions of years, have confirmed Einstein's time dilation with extraordinary precision, even detecting tiny differences in the flow of time between clocks placed just centimeters apart in Earth's gravitational field. Gravitational wave observatories like LIGO have confirmed that spacetime itself can ripple and stretch, treating time as a genuinely physical, bendable dimension rather than an abstract backdrop. The Event Horizon Telescope's images of black holes have given us direct visual evidence of regions where time, according to general relativity, slows to a near standstill for outside observers as objects approach the event horizon. Meanwhile, physicists working on quantum gravity, attempting to merge general relativity with quantum mechanics, have proposed frameworks in which time itself might not be fundamental at all, but rather an emergent property arising from deeper, timeless quantum relationships, an idea explored in approaches like loop quantum gravity and the problem of time in canonical quantum gravity. These remain theoretical and unconfirmed, but they suggest something remarkable. Time, the thing that structures every second of your conscious experience, might not be a basic ingredient of reality at all. It might be something that emerges, the way temperature emerges from the motion of countless individual molecules without any single molecule itself possessing a temperature. What this means for you. If the block universe picture is correct, then in some deep mathematical sense, you have already lived every moment of your life. Your childhood hasn't vanished into non-existence. It exists permanently at its own coordinates in space-time. Your death, whenever it occurs, already exists too at its own coordinates, just as real as this very sentence. That might sound bleak, but many physicists and philosophers find something quietly profound in it instead. If nothing is ever truly lost, if every joyful moment, every conversation, every sunrise you've ever witnessed remains permanently woven into the fabric of space-time, then the flow of time might be less like a river carrying things away and more like a spotlight moving across a landscape that was already fully there. Your conscious experience of now wouldn't be an illusion exactly, it would be something more subtle, a kind of window moving through a timeless structure, creating the story of a life through the sequence in which it experiences the story's already existing chapters. We still don't know for certain which picture of time is correct. What we do know is that the answer will not just change physics textbooks, it will change how we understand loss, memory, mortality, and the meaning of the word now. the ending that isn't an ending. Consider this. Somewhere in the four-dimensional structure of space-time, if the block universe is real, there exists a fixed, permanent point representing the exact moment you were born. And somewhere else in that same structure, equally fixed, equally real, exists the moment you will die. Between those 2 points lies everything you will ever do, feel, love, and lose, not flowing toward you from an open future, but already standing there waiting, the way the final chapter of a book already exists on the shelf before you've read it. And if that's true, then the sentence you're hearing right now in this exact instant isn't really happening. It already has. The deeper we look into the nature of time, the more it stops looking like a river and starts looking like something far stranger, far older, and far more permanent than anything we ever imagined.